So we'll pick up from there. We were trying to find the Reynolds number. It's rho VD over mu. We know the density, rho, is 999.1 kilograms per meters cubed, times the speed, which we've now found to be about 4.584 meters per second. And our diameter, we are going to assume that it's exactly the nominal value, because they've not told us much else about the pipe here. So 0.05 meters, and then the mu value, 1.138 times 10 to the minus 3 kilograms per meter per second. Now, as always, we want to write these units out to make sure they work. This should be a unitless quantity. This is the whole purpose of dimensionless quantities, Buckingham-Pi theorem, for us, chapter 7. This should be a dimensionless quantity, and it appears that it is. It appears the units are all going to cancel out. Yes, per seconds go away. I've got the same number of meters on top as I do on bottom, and the kilograms go away. So, we should just be looking for a number here. So the Reynolds number, well, let's just do this. I'm going to do the viscosity because I'm using just a standard scientific calculator. I'm going to do the viscosity. I'm going to do the denominator first. So that's 1.138 to the times 10 to the minus 3. Okay? And I'm going to invert that. Now, those of you that are not used to using a scientific calculator, like, what the heck did I just do? Well, I just took this and moved it up to the top. Right? So I'm going to multiply by the inverse of this. Anyway, times 999.1 times 4.584 times 0.05. That should be my Reynolds number. About 201,000, give or take. However you get from here to here is just... Now, what does this tell us? This tells us something. What do we need the Reynolds number for? Oh yeah, the Reynolds number tells us whether we're dealing with, or gives us a prediction of whether we're dealing with laminar or turbulent flow, because how we're going to find the viscous effect is going to depend on whether I'm dealing with laminar or turbulent flow. I would very much expect the flow through this pipe to be turbulent. Right. Turbulent because this is in excess of at least 4,000. 2,300 is a pretty good assumption. You get over 4,000, it's almost guaranteed in pipes. So we've got turbulent flow. That means we've got appropriate models, or we've got a certain set of models we can use to find that friction factor. Okay, now, how do we do that? Well, we said there's a few options. One of the most common options we will use is what we call the Moody diagram. So the Moody diagram says, well, give me your Reynolds number, which we've found to be 200,000. This is 2 times 10 to the 5. Yep. Alright, so if I've got, let me make sure. There we go. Ink. No, not on this frame. Here we go. This frame. Ink. Yeah, 2 times 10 to the 5 is my Reynolds number. So I'm going to draw a line. I've got a stylus here I grabbed just for this very occasion. So I've got a Reynolds number, 2 times 10 to the 5, 200,000. So I plot that in here. I need to know what my epsilon over d value is. What is my relative roughness value? Well, remember we found, and I borrowed, I do need a source there. I borrowed this from another instructor. Let's see here. Epsilon over d. We said epsilon was 0.002 millimeters. I need that in meters. So that's point, and I've got, what we've got, 5 zeros and a 2. 0.5 zeros and a 2 divided by 0.05 meters. Now to give you my epsilon over d values. It's going to be pretty small, right? No. Divided by 0.05. It's going to be 4 times 10 to the minus 5, or that is 0.00004. 4 zeros and a 4. And I need to know that because I need to know on my Moody diagram which one of these I'm going to trace. Well, I don't have, again, notice, 4 zeros and a 4. Well, I've got 4 zeros and a 1. I've got 4 zeros and a 5. I don't have 4 zeros and a 4. But notice what happens. So it's going to be closer to this line. Notice what happens. They all kind of cram together. So it's going to intersect right in there somewhere. So my F value, my Darcy friction factor, is going to be somewhere between 0.02 and 0.015. This is a logarithmic scale. This appears to be between 0.016 and 0.017, as best I can tell. So the Moody diagram is not going to give you a lot of precision, right? So the Darcy friction factor, well, let's just do it this way. Let's say Reynolds number and epsilon over d, right? 2 times 10 to the 5 and 0.0004. I'm showing a lot of detail here. These two together will give you a friction factor of, we said, about 0.016, and I'm going to say 5. It's between 1.6 and 1.7. And that's, well, let's specify how we got that, because there's a number of ways I can get that. There's a couple of equations we can use to get that as well. We're going to say we're using the Moody diagram to get there. And this is a Moody diagram. Using the Moody diagram to get there. All right. What the heck are we looking for? What are we trying to do here, Steve? Remember, we're trying to find the pressure loss, eventually the head loss, and eventually the power input required to overcome this thing. Okay. Well, we said the pressure loss, I need the Darcy friction factor, density, L over D, V squared over 2. And I've got all of those except for the Darcy friction factor. I now have the Darcy friction factor. So I should now be able to find the pressure loss, which again we said is F, L over D, rho, V squared over 2. So now I've got all those quantities. The pressure loss is going to be 0.165. L over D, we said it's a 30-meter pipe divided by 5 centimeters, so it's 0.05 meters. Goodness, density, we said was 999.1 kilograms per meters cubed. We said the speed, we found the speed to be 4.584 meters per second. That's going to get squared and divided by 2. How are we on time? Good on time. All right, let's see how we do here. 0.0165 times 30 divided by 0.05 multiplied by 999.1 multiplied by 4.584 squared divided by 2. All right. Now that's a big number, right? 103,921. I'm writing too many digits here. Now let's look at the units. Let's see, the meter's going to go away. I've got kilograms. That's not going anywhere. kilograms per meters cubed, meters squared per second squared. Okay, this looks a lot like a Pascal to me. This is kilograms per meter per second squared. So you can check that out. That's going to be 103.9 kilopascals. That's what that's going to translate into. How do I know that? Well, kilogram meter per second squared is a Newton. So one of the meters is going to go away. I've got kilogram. Basically, I've got Newton per meter squared. That's a Pascal. So there's one answer. Problem also asked for a couple of other things. It wanted to know the head loss. Well, the head loss is going to be the energy loss divided by gravity. And the pressure loss is going to be the energy loss multiplied by density. Well, I know the pressure loss. So to get the head loss, the head loss is just going to be the pressure loss divided by density and divided by gravity. Or it's also FL over D, V squared over 2G, whichever way you want to do it. I've already got the pressure loss, so I'm just going to divide by density and divide by gravity, and that's going to give me my head loss. So I'm going to leave it in base units, though. I'm going to say 103,921 kilograms per, oh goodness, what have I got? Meter second squared is what this translates into. Divided by 999.1 kilograms per meters cubed. And divided by G, 9.81 meters per second squared. So my head loss is going to be 103,921 divided by 999.1 divided by 9.81. About 10 meters. 10, well, almost 11 meters. 10.6. The kilograms go away. Let's see. I've got per meter squared on the bottom. That goes to the top. That's meters squared divided by meters. That's meters. The per second squared goes away. That's 106. I'm sorry, 10.6 meters. Here's my second answer. So to overcome this loss, if we allowed the pipe to drop, say, over this 30-meter length, if we allowed the pipe to drop almost 11 meters, then we would not notice any difference. That's what the head loss represents, is how much, if we try to measure that energy in length, how much energy does that represent? Well, it would represent the same energy you would gain by dropping 10.6 meters. That's how much energy you're losing as a result of fluid flowing through this pipe and the viscous effects associated with that. Okay. Now, the last thing the problem asks for is what is the power input required to overcome. Page 2. I want to know what is the power input required to overcome this loss. Well, if we go back and look at the general energy equation, that's the power input plus, let's just do this. Let's say that general power input is going to be the mass flow rate times the energy loss. Okay? And we could find the energy loss. We could also find, or we could say, well, this is, there's my time. So we're going to pick up, that's not a bad place to stop. We'll pick up the next video there. Loud pop.